Hey folks, Bill Armstrong here. Thought we'd take a look at some of the solutions for some of the problems that I'd given you in the sample test for test 3 here in college algebra. And I'm not going to do a worked out solution for all of them. You do have the answers for most of the sample test items. But I thought we'd look through, well, we'll do most of them that's on the sample test. First one I thought we'd look at is number 3. Here I gave you a function, x to the 5th plus x cubed minus 2. And in part A, I did ask you to use synthetic division to divide this function by the binomial x minus 2. So in part A, when you're going to do synthetic division to divide, shorthand here, divide it by the binomial x minus 2, remember the process of synthetic division. You want to list the coefficients of the function that we are, we're going to be dividing. So I start listing the coefficients of that function. So x to the 5th, the coefficient is 1. Now the x to the 4th term, since it's not in there, that means the x to the 4th term has a coefficient of 0. And I have to include that 0. So here's the coefficient for x to the 4th, 0. The coefficient for the x cubed term is 1. Now the x squared term isn't there. That means it has a coefficient of 0, and I have to list that. The x term isn't there, so that means it too has a coefficient of 0, and I have to list it. And then we don't forget the minus 2 at the end. So these are the coefficients of the polynomial that I'm dividing, and then you make a line or a symbol like this, and out here we put what it is we're dividing by. Well, we're dividing by x minus 2, so I'll put a 2 here. Please remember the general form is x minus c. And it's the c that you put out here. So x minus 2, that's x minus c. If this had been x plus 2, then I would have had a negative 2 here. Because if it were x plus 2, to get an x plus 2 from the general form x minus c, c would have to have a value of negative 2. X minus negative 2 would give you an x plus 2. But for this one, it was nicely set up as x minus c, so I have a 2 here. And then you remember your process of synthetic division. You start off, you bring this 1 on down. Then you take the 2 times the 1, and 2 times 1 is 2, and you put 2 here. And then you add 0 plus 2 is 2. Repeat the process. Now it's 2 times 2, which is 4. You put 4 here. 1 and 4 is 5. 2 times 5 is 10, so you put 10 here. 0 plus 10 is 10. 2 times 10 is 20. Add 0 and 20 is 20. And then finally, 2 times 20 is 40. And then you add and you get a 38. And, what I want you to notice here is this tells you the quotient. This is the answer, if you will, when you do this division. And this is the remainder. So when you take this function and divide it by x minus 2, right here's what you get. Now these are the coefficients of what is in the quotient. And when you do the division, these are the coefficients of the variables that will be in the quotient. Easy way to remember it, since we were dividing by x to the 5th plus x cubed minus 2, your quotient will have a degree that starts off 1 less than what you're dividing into. So since the degree of this polynomial was 5, this coefficient matches up with a term that would have a degree of 4. So my quotient is 1x to the 4th, and then plus a 2x cubed, plus a 5x squared, plus 10x plus 20. And then this number here, that is the remainder. So when you take this x to the fifth plus x cubed minus 2 and divide it by x minus 2, you're going to get this polynomial here. That is your quotient. That's the quotient. And you get a remainder of 38. So then in part B, I have to erase. But in part B, I'm going to try to put part B in here. I'm going to leave this work up. But in part B, I asked you to write, I asked you to use the result of part A, which is right here, to write the function in the form f of x equals x minus c times q of x plus r. So this is our function. We just did the polynomial, or we just did the synthetic division. So we should be able to take this function and write it in the form x minus c. That's what we were dividing by. X minus 2. That's our x minus c. Q of x, that's our quotient. Well, here's our quotient, so let's write it down. The quotient is x to the fourth plus 2x cubed plus a 5x squared plus a 10x plus 20. And then it says plus r. That's the remainder. We had a remainder of 38. So plus 38. And this is all there is to your answer in number 3, part B. We've written our polynomial that we were given in the form x minus c times the quotient, which is what we found in part A, doing synthetic division, plus the remainder, which we found that also in part A, using synthetic division. And that's it for number 3. Hey folks, thought we'd take a look at number 4. In number 4, I asked you to use the factor theorem to determine if x minus 7 is a factor of f of x equals x to the fourth minus 45x squared minus 196. Keep in mind, just to use the factor theorem, and again, a lot of these little theorems are predicated on the form x minus c. X minus c. Notice that 7 is what c would be. So to use the factor theorem, you just simply evaluate the function at 7. So we're going to evaluate this function at 7. That means we put 7 in for all the x's. And when we put 7 in for all the x's, we get 7 to the fourth minus 45 times the 7 squared minus a 196. Okay, I'm glad I have a calculator to crank through those calculations. And when I use my calculator, and I do 7 to the fourth minus 45 times 7 squared minus 196, I get a value of 0. Now, getting a value of 0, this tells us a lot of stuff, folks. Getting a value of 0, well, first off, it tells us that 7 tells us that 7 is a 0 of the function. F of 7 equals 0. That tells us 7 is a 0 of the function. If we know 7 is a 0 of the function, that tells us x minus 7 is most definitely a factor. Keep in mind, if you know a 0, you know a factor. If you know 7 is a 0, you know x minus 7 is a factor. If you know 5 is a 0, then you know x minus 5 is a factor. If you know if you know negative 3 is a 0, then you know x plus 3 is a factor. It's a nice relationship. Also, if you know a factor, you know a 0. But you weren't asked that here. You were just asked, is x minus 7 a factor? And since we have f of 7 to be 0, that tells us 7 is a 0, which tells us x minus 7 is a factor. So the answer for number 4 is, yep, x minus 7 is a factor of the polynomial. And that's it for number 4. All right, hey, here, thought we'd take a look at number 5. Gave you this function, and I asked you to use the rational zeros theorem to list all of the possible rational zeros of this polynomial function. And then I have written, do not find the zeros. I'm just asking you to list all the possible rational numbers that could be zeros of this function. That's using the rational zeros theorem. Now remember, in using the rational zeros theorem, you're looking at the constant and you're looking at the leading coefficient. And what you're trying to do, or what you need to do, is you need to list all the factors of the constant 6 and all the factors of the leading coefficients. So here's how I organize my work. I'm interested in simply the integer factors of the constant 6. And those integer factors of the constant 6 and your rational zeros theorem is going to be called, they are the variable p. So let's list all the integer factors of 6. Well, we should have as the integer factors of 6 plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now let's get the integer factors of our leading coefficient, negative 4, and the integer factors of the leading coefficient 4, they comprise what we call the variable q. So the factors of negative 4, plus or minus 1, plus or minus 2, and plus or minus 4. And now your rational zero theorem tells you all possible rational zeros for this function have the form p over q. So since we have all the factors of p and all the factors of q, it's just a matter of writing down all the combinations of p over q. So here we go. Let's just start listing them. Now here's how I do it. I'm going to take this first factors of p plus or minus 1, and I'm going to do p over q, p over q, p over q. So that will give me plus or minus 1 over plus or minus 1, which is just plus or minus 1. Then plus or minus 1 over plus or minus 2, well, that gives me plus or minus 1/2. Then next I have plus or minus 1 over plus or minus 4, which is just plus or minus 1/4. Okay, so I've taken care of all combinations where this would be in the numerator of p over q. So I move to the next p, and it would be this over this, this over this, this over that. So plus or minus 2 over plus or minus 1. Well, that's plus or minus 2. Then I'd have plus or minus 2 over plus or minus 2. Well, plus or minus 2 over plus or minus 2 would simplify down to plus or minus 1. I already have that listed, so I don't have to list it again. It's already in my list. Plus or minus 2 over plus or minus 4. Well, that would simplify down to plus or minus 1/2. I already have that listed. I don't need to list it again. So I've done every combination of having the plus or minus 2 over each of these q's. So now it's time to move to the next value of p and do this over this, this over this, this over this. So to get started, plus or minus 3 over plus or minus 1. I don't have that listed, so I better put it in here, plus or minus 3. Then we have plus or minus 3 over plus or minus 2. Well, that's plus or minus 3 over 2. And then finally, plus or minus 3 over plus or minus 4 gives us plus or minus 3/4. Now I move to the last p in my list, and I have to do this over this, this over this, and this over this. So starting off, I have plus or minus 6. Plus or minus 6 over plus or minus 1. So that's just plus or minus 6. Notice plus or minus 6 over plus or minus 2. I already have that listed. That simplifies the plus or minus 3. And then finally, plus or minus 6 over plus or minus 4. That would reduce down to plus or minus 3/2. And I already have that listed, so I don't have to list it again. And this would be the answer to number 5. Those are all the possible rational zeros for this polynomial. If this polynomial has a rational zero, it's in this list somewhere. And that's all you were asked to do for number 5. So that's it for number 5. All right, folks, here number 7. Gave you this rational function. And I asked you to determine the vertical and horizontal asymptotes for the rational function. The first thing I'll look at real quickly is the horizontal asymptotes. Remember, for the horizontal asymptotes, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is the x-axis. It's the line y equals 0, also known as the x-axis. So here the degree of the numerator is 1, the degree of the denominator is 2. So since the degree of the numerator is less than the degree of the denominator, we have the horizontal asymptote is the line y equals 0. Again, that's also known as the x-axis. Now remember, if the degree of the numerator is equal to the degree of the denominator, so they have equal degrees in the numerator and denominator, then the horizontal asymptote is the line y equals leading coefficient of numerator over leading coefficient of denominator. And then the other possibility is if the degree of the numerator is larger than the degree of the denominator, then you don't have a horizontal asymptote. You have what's called a slant asymptote. But here we had degree of the numerator less than degree of the denominator. In any situation that occurs, boom, that's your horizontal asymptote. Now to get the vertical asymptotes. To get the vertical asymptotes, what you really would like to do is to get your denominator as factored as possible. And I think, if we do this up here, I think this denominator, let's see if I factor it, factors of 32 that add up to negative 12. I think that's what you'll see the denominator factors to, x minus 4 times x minus 8. Now the game is you determine those values of x that makes the denominator 0. And it looks like, from the factored form, the values of x that make the denominator 0 are x equals 4 and x equals 8. Those two values of x, which would not be in the domain of the function, those two values of x, 4 and 8, are doing one of two things for the graph. It's either producing a vertical asymptote or there's a hole in the graph. If it is producing a hole in the graph, whatever value of x makes the denominator 0, it would also make the numerator 0. So in other words, any value of x that makes the denominator 0 and the numerator 0, that value of x would be producing a hole in the graph. Any value of x that makes the denominator 0, but the numerator is not 0, that's producing a vertical asymptote. So here, we have two values of x that's making the denominator 0. The values of x that are making the denominator 0, x equals 4. And notice, if you have 4 in here in the numerator for x, 4 minus 64, that's definitely not 0. That's like a negative 60. So since this is a value of x that makes the denominator 0, and the numerator is not 0, that's producing a vertical asymptote. X equals 8, that makes the denominator 0, but the numerator is not 0 for x equals 8. That means x equals 8 is also producing a vertical asymptote. So in number 7, you have a horizontal asymptote at y equals 0. You have two vertical asymptotes, x equals 4 and x equals 8. And that's all there is to number 7. Hey folks, here in number 8, you're asked to solve this equation. And, my advice on solving this equation is to start off by rewriting 1/3 as 3 to the power. Now, 1/3 is 3 to the negative first. And we shan't forget there's that exponent of 6x plus 5. So that's rewriting 1/3 as 3 to the negative first. And let's rewrite 9 as a 3 squared. And now we use properties of exponents. If you have a 3 to the negative first, which is raised to the 6x plus 5, you can multiply those two exponents together to get 3 to the negative 6x minus 5. And the same deal over here. You have a 3 squared raised to the x minus 4, so you can multiply those two exponents to get 3 to the 2x minus 8. And then we just utilize that one nice little property. I call it the preservation of equality property. I don't know what your book calls it. But you have an equation. You have an exponential expression equaling an exponential expression. The bases are the same. They both have a base of 3. In order for this equation to be true, since they have the same base, the exponents must be equal. So just set the exponents equal to each other and continue to solve. I mean, everyone will solve this differently. I'm going to pull the problem up here because I'm running out of room. I would subtract 2x from both sides. So that gives me a negative 8x. And then I would add 5 to both sides. So if I add 5 to both sides, I have negative 8x equals negative 3. And then finally, I would divide both sides by negative 8 to get x equals 3/8 as the solution to this equation. So again, the key to solving this equation was I had the ability to rewrite this base, or this 1/3, as an exponent with a base of 3, and I had the ability to rewrite the 9 as something with a base of 3. That's it for number 8. Hey folks, here in number 9, I guess we're dealing with some rabbits. It says a rabbit population of a certain forested area grows at a rate of 8% monthly. In September, there were 290 rabbits, and the population can be modeled by this function. And you're asked to determine how many rabbits should be expected by next September. So let's think, next September, since T is telling us something about months, next September, so that would be a year. So 1 year, next September, 1 year, well, that's 12 months. So that means all we have to do is evaluate this function at 12. So we evaluate the function at 12. And again, I am so happy to have a calculator where I can multiply this all out on the calculator. And if you do this on the calculator, you get something close to 752.5012254. Okay, now the directions did say to round your answer to the nearest whole number. Well, now think about why we would want to do this. F of t represents the number of rabbits. We just found how many rabbits will be running around in this forest next September. It doesn't make sense to have a 752.5 rabbits. I mean, what does a half a rabbit look like? We don't do that. That's why we're going to round it to the nearest whole number. So I would have my answer 752.5. That rounds to the nearest whole number of 753. So if in September they said there were 290 rabbits, next September, I have the answer here. There's going to be 753 rabbits. That's it for number 9. All right, hey folks, here in number 10, it's another exponential equation you're asked to solve. And I'm going to attack this very similarly to what I did in number 8. In other words, I'm going to try to rewrite each side of the equation with the same base of e. Notice my left side is already written as a base of e. But over here, this 1 over e to the 4th. Well, 1 over e to the 4th is really e to the negative 4th. So I'll rewrite 1 over e to the 4th as e to the negative 4th. And then very similar to number 8, I can now use a property of exponents and multiply those two exponents together to get e to the negative 4x minus 12. And just like what we saw in number 8, we have an equation here where we have a single exponential equaling another exponential, and the bases are the same. So in order for this equation to be true, the exponents have to be equal. And, we solve this. I'd probably add 4x to both sides, and then I would add 3 to both sides, and then divide both sides by 5 to get x equals negative 9/5. That's my answer for number 10. And that's it for number 10. All right, hey, here in number 11, got a lot going on. It's like 4 parts. It starts off by saying an investor puts $3,000 into a savings account, and the savings account accumulates at an interest rate of 1.3% interest compounded continuously. Then it says the amount in the account after t years is given by the function a of t equals 3,000 e to the 0.013 t. And let's see, part A. Does this function model exponential growth or exponential decay? Well, quite simply, it's exponential growth. We know it's exponential growth because the base is e and the exponent is positive. That's it. Part B, you're supposed to evaluate a of 0 and then comment on what does that quantity a of 0 represent in this situation. Well, if you evaluate a of 0, so you put 0 in for the t's, well, 0.013 times 0, if you multiply this together, you get 0. E to the 0 is 1. 3,000 times 1 is 3,000. Now think about this. That's not a surprise. When you put 0 in for t, and since in the problem we were told t represents the number of years. So if t has a value of 0, we're talking about no time has elapsed. So putting 0 in for t should match up with how much money was initially deposited into the account. A of 0 gives you the amount that was initially deposited. What was initially deposited? $3,000. And intuitively that should make sense because the problem starts off by saying an investor puts $3,000 into a savings account. So if they put $3,000 into the savings account, we better get A of 0 to be 3,000. So now for part C, you're asked to solve an equation and get the exact answer algebraically, and then use your calculator to get a decimal approximation of the answer. So let's see, part C, try to fit it in over here, folks. You're asked to solve A of t equals 6,000. All right, well, here's your function A of t. So basically it's saying put 6,000 in here for A of t and then solve. So we put 6,000 in here for A of t, and we have 6,000 equals 3,000 e to the 0.013t. So to solve this equation, the first thing I would do is just divide both sides of the equation by 3,000. And 6,000 divided by 3,000 gives me a 2. It helps if I remember the equal sign. So we have 2 equals 0, or e to the 0.013t. All right. Next, I'm going to take this exponential equation and rewrite it as a logarithmic equation. It really is an important skill to be able to go from exponential form to logarithmic form, and vice versa, from logarithmic form to exponential form. Here I have an exponential equation, so I'm going to write that into the logarithmic equation form. And the logarithmic equation form for this equation is the natural log of 2 equals 0.013t. So I went from exponential form to log form. That's just an important skill to have. My final step in getting the exact solution is to divide both sides of this equation by 0.013. So I have natural log of 2 divided by 0.013, that is t. Folks, this is the exact solution. And we were asked, or I asked you here, to find the exact answer algebraically. Well, we did it. That is the exact answer algebraically. Then I said to use your calculator to get a decimal approximation. So this is where you fire up your calculator and you do natural log of 2 divided by 0.013. That will give you a decimal approximation. And when you take your calculator and do natural log of 2 divided by 0.013, you will get t to be about 53.32. So this is the approximation that you get using your calculator. Exact answer, approximate answer. And then in part D, it says, what does your solution to this equation? What does that solution mean, given this problem situation? Well, notice, if you're saying A of t is 6,000, that's basically saying, how long will it take, because t represents time in years, how long will it take for that $3,000 you invested, how long will it take it to become $6,000? So how long will it take your $3,000 to grow to $6,000? Or in other words, how long will it take your $3,000 to double to $6,000? And when we solve that equation, we have this as an approximate answer. It's going to take approximately 53.32 years for that $3,000 to grow to a value of $6,000. And that's it for part D. So, a lot of parts to number 11, but that's it. That's it for number 11. All right, hey folks, here at number 13, I gave you a logarithmic function. I asked you to determine the domain of the log function and, of course, write your answer using interval notation. Okay, remember with a log, when you have a log function, the domain has to be greater than 0. You can't find the log of 0. You can't find the log of a negative number. So when I look at this stuff in here, x plus 5 over x minus 4, I guess I'm going to say, it has to be positive. What's in there? X plus 5 over x minus 4. We have to guarantee for any x we pick, we have a positive result. As a quick observation, very quick observation, you should immediately see that x can't be 4. 4 is not in the domain. Because if x were 4, the denominator would be 0, and we know we don't divide by 0. We can't have 0 in the denominator. So if, again, this is an if I had seen the function, let's just say log of 2 over x minus 4, and I'm asked for the domain, I know 4 is not in the domain. And then I also know I can't have any negatives in the domain. I can't do the log of a negative number. So maybe I would immediately have that as the domain. But I don't have that. I have this that I'm trying to find the domain for. I know 4 isn't in the domain. But I have to guarantee for values of x that this rational expression is greater than 0. Now this should look somewhat familiar. It's like solving a rational inequality. You've done that earlier in this course. You've solved a rational inequality. And I'm going to take you through the process I remember doing on a prior test, doing a solution for a sample test. And, that's like making the following, system. Make your real number line. What's the real number line? X. Make sure numerator and denominator are completely factored. They are. On your real number line, list those values of x that will make the numerator 0 and the values of x that will make the denominator 0. Well, negative 5 makes the numerator 0, 4 makes the denominator 0, and then this is the bookkeeping, or organizing our work, so to speak. Put the numerator, all factors of the numerator here, all factors of the denominator, list them over here, and then I think I showed you that I kind of make dashed lines. And then I find where the zeros are. In other words, x plus 5 has a value of 0 at negative 5. X minus 4 has a value of 0 at 4. And then hopefully, this is coming back to you. You remember doing this, that you pick numbers in these intervals and test them. In other words, pick a number in this interval from negative infinity to negative 5. I don't know, negative 6 is in that interval. Put negative 6 in here for x. Negative 6 plus 5 is negative 1. But more importantly, it was negative. Negative 6 minus 4 is negative 10. More importantly, negative. Pick a number that you know is definitely in this interval, from negative 5 to 4. I don't know, 1. 1 is definitely in that interval. Put 1 in here for x. 1 plus 5 is 6. Positive 6. So more importantly, positive. And then put that 1 in here for x. 1 minus 4 is negative 3. Negative. And then finally out here in this interval, from 4 to infinity, pick a number. 5. 5 is definitely in that interval. You put 5 in here for x, and you get 5 plus 5 is a positive 10. Positive. 5 minus 4 is 1. Positive 1. And This sign diagram is what tells us, what's happening. It's telling us that x plus 5, on the interval negative infinity to negative 5, x plus 5 will be negative. On this interval, it'll be positive, and on this interval, it'll be positive. So look at what you're asked. You're being asked, when does x plus 5 divided by x minus 4 give you a positive number? When is it greater than 0? Well, on the interval negative infinity to negative 5, x plus 5 over x minus 4 will be a negative divided by a negative. Negative divided by a negative is positive. On this interval, it would be positive divided by a negative. Positive divided by a negative is negative. And finally out here, it's a positive divided by a positive, which is positive. And it's this line here that should answer the question. We want to know, when is this x plus 5 over x minus 4 greater than 0? Because we can only do the log of positive numbers. So when is it positive? When is it greater than 0? Well, in this interval and in this interval. So my answer, the domain in interval notation, will be negative infinity to negative 5. Don't include the negative 5. You can't include the negative 5 because at negative 5, this would be 0. You can't do the log of 0. And, oh, here's another positive. That's another area. This is another interval where that quotient is positive. So then it will be union with 4 to infinity. So that is the answer to number 13. The domain of this logarithmic function is negative infinity to negative 5, union with 4 to infinity. That's it for number 13. Hey folks, here in number 14, I asked you to use the properties of logarithms. It says use the properties of logarithms to expand the logarithmic expression as much as possible. So here's your logarithmic expression, natural log of e to the 5th over 8. And I think the first property we would use is the property that says when you have the log of a quotient, you can rewrite it as a subtraction statement. So I'm going to rewrite this as the natural log of e to the 5th minus the natural log of 8. Almost done. Natural log of e to the 5th, there's a property that tells me the natural log of e to the 5th immediately simplifies to 5. And that's because with natural log, the base is e. And well, here's an e. So I can use that property that tells me that it simplifies down to 5. And that's it. That's number 14. So let's go ahead and do number 15 right here next to 14. And at 15, you're given the logarithmic expression 1/5 log base 4 of x plus log base 4 of y and then O minus a 5 log base 4 of x plus 1. Barely fit it on. Now here, it's kind of like working number 14 in reverse. Because here the directions are, use the properties of logs to condense that logarithmic expression. And we're going to condense it to a logarithmic expression that's just a single logarithm. And it has a coefficient of 1. So, let me draw a little line down here. I would probably begin this one by looking inside the parentheses and using that property of logs, that law of logarithms that says when you have the log of a product, you can rewrite it as a sum of 2 logs. Well, here I have a sum of 2 logs. They have to have the same base, and they do here. So I can use that property and rewrite this as 1/5 log base 4 of x times y. It's using a property of logarithms. And then minus 5 log base 4 of x plus 1. The next thing I would do is, there's that property of logarithms that says if you have the log of like x to the r, you can move that r out front and have it as r log x. I'm going to use that property, but I'm going to get this 1/5 back into the exponent position, and I'm going to get this 5 back into the exponent position. So that will give me log base 4 of this xy, and it has an exponent of 1/5 minus log base 4 x plus 1 with an exponent of 5. So that's using another law of logarithms. Next, I see I have a subtraction. So since I have a subtraction, I could rewrite that as a division. So log base 4 of xy to the 1/5 over x plus 1 to the 5, to the 5th power. And then the only other thing I guess we could do is we have this xy to the 1/5 power. So if we want, we can really make this look nice by rewriting the 1/5 power as the 5th root. And that would be it. Yeah, this would be fine. I'd be happy with this as an answer. And this is, of course, fine because it's equivalent. But that's number 15, taking a logarithmic mess using properties of logarithms and condensing it down to a single log expression, and we have a coefficient of 1 here. So that's it for 14, and that is it for 15. Hey folks, here in number 16, you're asked to solve a logarithmic equation. So again, I'm going to just kind of crank this out pretty quickly. When you have a log equaling a log, if the bases are the same, and they are here, this is a base of 8, this is a base of 8, the only way you can have this log expression equaling this log expression is if those two pieces are equal. So in order to have this equation be a true statement, you must have 2x plus 5 equaling 3x minus 8. And what I would do here is I would probably subtract 2x from both sides and add 8 to both sides. And I immediately have the solution, x is 13. And that is it for number 16. All right, hey, here in number 17, I gave you a couple of exponential equations to solve. I think we're just going to do part A. And part A, you're asked to solve 2 to the x equals 7. Well, this would be really difficult for me to rewrite 7 as 2 to some power. I can't do that off the top of my head. So what I would recommend doing here is taking the log of both sides of the equation. Now you could take the log of any base to both sides of the equation. You could do log base 5 of both sides of the equation if you'd like. I'm going to take the natural log of both sides of the equation. So when I take the natural log of both sides of the equation, check out what happens over here on the left side. X is in the exponent position. So you have the natural log of 2 to the x. We have that property of logarithms that says when you have an x in the exponent position, you can move it out front. And that's exactly what I'm going to do. And then next, to solve for x, divide both sides by the natural log of 2. And that's the exact solution. X equals the natural log of 7 divided by the natural log of 2. Now, if you use your calculator, you'll get a decimal approximation of somewhere around 2.8074. And that's it for number 17, part A. All right, folks, here in number 18, I gave you a couple of logarithmic equations and asked you to solve them. Here I thought we'd look at 18b. 18a is very similar to number 16. So in 18b, you are given, so this is b, you're given log base 2 of x minus 2 plus log base 2 of x plus 2 equals 5. So to solve this equation, well, the first thing I would do is on the left side, I have the log, I have an addition. I'm going to use a property of logarithms and rewrite it as the log of a product. So I'm going to take the left side and rewrite that as log base 2 of x minus 2 times x plus 2 equals 5. Okay, now as I mentioned earlier, it's really important for you to be able to take an equation from exponential form, put it into log form, and vice versa. If it's in log form, to put it into exponential form. Well, here we have an equation. We see log involved. I'm going to rewrite this into exponential form. So to rewrite this into exponential form, the base is 2. I would have 2 to the 5th power equals x minus 2 times x plus 2. Okay, now it's kind of like a Nike problem. We should just do it. 2 to the 5th is 32. Foil this out over here and you get x squared minus 4. And then simply add 4 to both sides. And then take the square root of both sides. And you get plus or minus 6 is equal to x. So it looks like you have two solutions. X equals 6 and x equals negative 6. Looks like there are two solutions, but we only have one solution to this equation. You should at least do a very brief check of your answers. Look what happens if you put negative 6 in here for x. If you put negative 6 in here for x, and negative 6 minus 2 is negative 8, can you take the log of a negative number? That's right, you cannot take the log of a negative number. So since you can't take the log of a negative number, and when we put negative 6 in here for x, we got a negative number, that is not a solution. It's called an extraneous solution. It's a bogus solution. This is the only solution for number 18, part B. And that's it for 18. All right, folks, here finally number 19. Sarah's got $2,000. And she's going to invest it at 4.75% interest. In part A, we want to know how long will it take before she has $3,200 if the interest is compounded monthly. Part B, how long will it take before she has $3,200 if the interest is compounded continuously? So in part A, you're going to need this formula. Whereas in part B, since it's compounded continuously, you're going to use that formula. Now let's look at everything we know. We know Sarah has $2,000 she's going to invest. That $2,000, that's her principal, so that's the P. So we'll put $2,000 in for the P. We know the rate. Well, we thought we knew the rate. We do. It's 4.75%. So we rewrite that as a decimal, 0.0475. Compounded monthly, so n is 12. And that means this n is 12. We don't know t, because t is the time in years. And that's what we're trying to find. We're trying to find how many years, or how long will it take the $2,000 to grow to $3,200. $3,200 goes in here for A. So let me get this line back now. So this is the equation we need to solve in part A. In part B, it's compounded continuously. We use this formula. We have to solve this equation. Okay? Either way, I think the very first thing you should do in trying to solve is to divide both sides of the equation by 2,000. And 3,200 divided by 2,000 gives you a 1.6. And so we have 1.6 equals. Now folks, if you're going to use your calculator to do 0.0475 divided by 12 and then add 1 to it, do not round that. You don't round in the middle of solving the problem. The only time you can round is at the very end. So if you do 1 plus 0.0475 divided by 12, I mean, this is the ugly number you get. 1.003958333. Can't round that. You got to keep writing it down. Next, kind of looks a little bit like 18 part B when we were solving. We got to get this out of the exponent position. I should take the log both sides of the equation. And again, like I did in 18 part B, I'll do the natural log. So I take the natural log of both sides. And I have to keep writing this big ugly number down. And then property of logarithms. I could take the 12t and move it out front. And write that big ugly number down yet again. And then I'm going to divide both sides of the equation by 12, the natural log of that ugly number. So that gives me the natural log of 1.6 divided by 12, natural log of this ugly number. I mean, look at that ugly number. That's what t is. That's actually the exact value for t. But why don't we use our calculator and get a decimal approximation now? And this is where we will round. And if we do it, and we do it correctly on the calculator, crank this through the calculator correctly, we get t to be pretty close to 9.914, and that would be years. So if it's compounded monthly, this is the compounded monthly, it's going to take about 9.914 years for Sarah's $2,000 to grow to $3,200. Okay, now in part B, we have it set up. It's compounded continuously. Start off the same way as part A. Divide both sides by 2,000. So you have 1.6 equals E, not to this mess. And I have an exponential equation. It's pretty easy for me to write that as a logarithmic equation. It's the natural log of 1.6 equals 0.0475t. Then divide both sides by 0.0475. And that's the exact value for t. But let's use our calculator and get a decimal approximation here. And if you crank this through the calculator correctly, you should get t to be about 9.895 years. So if she invests her money, her $2,000 in an account earning 4.75% interest compounded continuously, it will take about 9.895 years for her money to grow to $3,200. And intuitively, that should make sense. Compounded continuously at the same interest rate, compounded continuously, it should take a little less time than compounded monthly. And that's it for number 19. Hopefully you're feeling pretty good, feeling confident for this test. This test is a little longer than the other test. There's a little more material. But as always, there's no time limit on the test. So take your time, prepare hard, study hard, and hopefully you're feeling pretty good. Thanks for watching.